All right, well, welcome back, everybody. I hope you're enjoying the smorgasbord so far. We're going to be blessed to learn more about limestone. And this is Ellen McHenry, and she is the glue that holds us all together. Professional artist, science writer, and independent researcher. And she was actually interviewed on Real Science Radio. If you get time, might want to check that out. But without further ado, here's Ellen McHenry.
Okay, thanks everybody for bearing with our little hiccups and stuff here. Um, we didn't expect to be doing this ourselves, and we all had a crash course in Zoom webinars in the last 6 weeks. So thank you for being patient. All right, so what I'm going to do, because I can't just use my PowerPoint like I did with the first presentation. Um, my PowerPoint crashed between the time that I recorded the video and anyways, I think I lost some of the slides. So what I'm going to do, I have all the slides on the backup video. So what I'm going to do is just play the backup video and I will narrate and tell you what's going on in each picture. So hopefully I can remember everything that's going on in each picture. I won't do as good a job as Brian Nickel in narrating that part, unfortunately, but I can, anyways, you can go to Brian's channel to hear it. So let's see. I'm going to try again to screenshot. Oh, first, I should say, hang on. So what I'm presenting is available as an ebook. What? Okay, there we go. For free download, if you go to the conference page where all the talks are listed, so right under this talk, there will be a link. And if you click on it, you should get a free copy of this paperback. Eventually, I hope to have it up on online booksellers, and you can actually have a physical copy. This is just a proof copy that I'm holding, and I'm still working through it. But you can have the digital copy. So there's extra information in the ebook. There's a lot of extra information in the ebook. So what I'm going to show you here is just the highlights of it. So there's a lot of it's worth paging through the ebook. There's also, I think, an outline available next to it. There should be a link for an outline to the talk, which is just this kind of boring, hitting the major points. Nothing pretty. First, what is limestone? Well, it's any rock that is made primarily of the mineral calcium carbonate, CaCO3. You see the molecule there, carbon, 3 oxygens, and a calcium ion. So sometimes there's other minerals mixed in, but if it's primarily calcium carbonate, then we classify it as limestone. And one way to test for this, if you're in the field, is you have a little vial of acid with you. You put a few drops of acid on the rock, and if it bubbles, making carbon dioxide bubbles, then you know it's limestone. A common type of limestone is I think, boring gray rock that has almost no fossils. And this is the kind of rock that surrounds me in central Pennsylvania. I took this photograph just down the street from my house at a limestone quarry. So yeah, I think this is pretty boring rock. And the quarry just crushes it up to make gravel landscaping rock. So they think it's pretty boring too, I guess. So they think that gray limestone gets its dark color from molecules of kerogen, which are carbon-based organic molecules, probably from decomposition of living things, plants, animals, algae. And this fits very well with the idea that limestone was made during the flood when there was a lot of decomposing things around. Some limestone is almost white and yet contains really nice fossils. So the color indicates that there was very little decomposition. And also the preservation of these beautiful fossils indicates that it was a very rapid burial with very little decomposition. And this fossil is from the famous Solnhofen limestone quarry in Germany. The same quarry also gave us the famous Archaeopteryx fossil shown on the right. So the most exquisitely detailed fossils in the world are found in limestone because it's a very fine-grained rock. And on the left, I think that's a crinoid. Marble can also be classified as a type of limestone because we think it started out as limestone, judging by its chemistry based on CaCO3, but then it was squeezed and heated and underwent metamorphosis, and the crystal size increased to where the crystals are actually visible, and that's what gives marble that sparkle, these large crystals. And of course, marble is very good for sculpting, for making nice buildings. Travertine is a type of calcium carbonate that precipitates out of hot water and forms these interesting crustal shapes around hot springs. Stalactites and stalagmites in caves are also usually made of calcium carbonate, again precipitating out of the water. Some limestone contains little spheres called ooids, so the rock is called oolitic limestone. This is a picture that was taken under a microscope. They sliced the rock so you could see a cross-section of the ooids. And you could see there's a core. The limestone was forming around something, sand grain or something. Some oolitic limestone has very large ooids, and some has very small ooids. And this looks like a really fine-grained rock, even though it has little ooids in it. And the fine-grained oolitic limestone is actually very good for building things, like this monument in Indianapolis was made out of oolitic limestone quarried in Indiana. The White Cliffs of Dover are made of chalk, which is an organic form of limestone, and I'm going to deal with this in a special section at the end. We're going to find out that organic limestone is primarily made of shells of little strange creatures like this called coccolithophores. Some limestone is made of a mix of calcium carbonate and magnesium carbonate, and it's called dolomite. Now, if the calcium carbonate is extremely pure, it can form a really nice crystal, like the rhombohedral shape shown here. This is calcite, and it looks sort of rectangular, but in real life it looks a little more squished. It's like a box where you pushed on one corner and kind of pushed it out of shape a little bit. And it can also form a crystal shape called aragonite, which looks nothing like the box shape. So it's interesting that the same mineral can form these two very different crystal shapes. And aragonite usually occurs in a high pressure situation. So I thought it'd be fun to take a look at some well-known limestone formations around the world, like the Rock of Gibraltar. The rock around Niagara Falls is limestone. It's sitting on a bed of shale, but the top part is all limestone. And I think it stretches down into southern Ohio. It's quite a large, flat area of limestone. The Stone Forest of China. Many layers in the Grand Canyon, like the Redwall limestone shown here. It has some iron in it, so it's kind of red. James Bond Island in Thailand. Many arches and caves along the seacoasts of Europe. The one on the left, the more kind of gray limestone. On the right, we have the real pure, might even be chalk, but very different look than on the left, but both limestone. The White Desert of Egypt, some really interesting eroded features. And also the pinnacles in Australia. So how do secular geologists explain limestone? Well, they say all limestone, or mostly all limestone, was formed in warm, shallow seas. And you'll see this phrase all the time. Every time they talk about limestone, it's a warm, shallow sea. So they think that all of the calcium carbonate came from the remains of marine creatures like clams and oysters and corals, because their shells are made of calcium carbonate. And sometimes we find clam shells embedded in limestone. So they find a clam in limestone, and then they take a flying leap of logic and assume that the clam made the limestone. So because these creatures require sunlight and warmth, then therefore the sea that they lived in had to be warm and shallow so they could get sunlight and live. So they think that then as these creatures died, their shells dissolved and broke up and sank to the seafloor and piled up and made the limestone layer. So in order for this to happen, they have to have the seafloor subsiding, sinking at the same rate that the limestone is building up. So the picture on the left shows you if the seafloor drops too slowly, well, the limestone is going to build up very quickly, and eventually it's going to stick out the top of the water and the creatures will die. On the right, if the seafloor goes too quickly, the water is going to get too deep and the creatures won't be able to get enough sunlight and they'll die. So we have to have this just so growth right in the middle with the seafloor dropping at exactly the same rate that the limestone is growing for millions of years. So here are 9 mysteries associated with limestone, and we'll see how well hydroplate theory does at addressing these. First, why wasn't the atmosphere poisoned by carbon dioxide when all the limestone formed? Now, we know that for every molecule of limestone that precipitates out of the water and makes rock, a molecule of carbon dioxide is released. Now, this isn't something that hydroplate theory made up. This equation is very well established. It's in all the books. Nobody doubts it. So you can see that the equation can go either way because the arrow, it's got 2 arrows, one on either end. When the equation goes from left to right, we start with water and carbon dioxide and limestone, and the water and carbon dioxide combine to form carbonic acid, which dissolves the limestone and goes to the right and makes an aqueous solution that has calcium ions and the bicarbonate ions in it. So when the equation goes from the right to the left, we start out with an aqueous solution containing calcium ions and the carbonate ions, and they join, and all the atoms rearrange themselves to form one CaCO3, one CO2, and one H2O. So on the right, you can see that there's 2 carbons. We have 2 of those HCO3s, so that gives us 2 carbons, and they have to go somewhere. So one of them goes to the limestone, CaCO3, and the other joins with oxygen to make the carbon dioxide. So then the question is, how much carbon dioxide would have been made if all the limestone on the Earth had been made right there at the surface and contributed carbon dioxide to the air and water? Well, this bar graph shows how much carbon is in various things, the atmosphere, animals, plants, coal, oil, the oceans. And notice that you have to multiply those numbers by 10 to the 15th to get the number of grams of carbon in those places. And carbon is used as a proxy for potential carbon dioxide. So you notice that limestone isn't on this bar graph, and that's because we're going to add all of these together and compare them to how much carbon is in limestone. So all combined, they make that little line there at the bottom. It doesn't even look like a bar, it's so short. So the amount of carbon locked up in limestone is far, far, far more than all other sources combined. And we can calculate how much carbon dioxide this would have been compared to the atmosphere, and it turns out this would have poisoned the Earth many times over. So this is a serious problem for any theory that has all limestone being produced on the surface. Second, why are limestone layers so incredibly flat? And of course, the best place to see this is the Grand Canyon. And, it's hard to imagine that there was no erosion over those millions of years. They say that these, warm, shallow seas were there forming the limestone. The same geologists will turn around and tell you that water cut the canyon in a few million years. So if water can do that kind of erosion in such a short time, how in the world was there no erosion over millions of years? Some of these layers stretch for hundreds of miles. They're part of giant megasequences that cover a fair portion of North America. Some layers of limestone are extremely pure. How could this possibly happen in a warm, shallow sea? You know that lake beds and sea bottoms, they always have this kind of mucky, oozy stuff that goes between your toes. A lot of it is clay particles, dirt. So to get this pure limestone, that means that the warm, shallow sea for millions of years had no dirt in it. It's really hard to believe. Fourth, why do layers of limestone alternate with layers of shale, sandstone, or even coal, none of which are products of a warm, shallow sea? So their explanation is, well, the ecosystems just changed. There was a warm, shallow sea that dried up. Then there was a forest that fell over and died and rotted and made coal. And then the ecosystem changed and it became a desert for a few million years and sand built up. And then it went back to a warm, shallow sea. And then it was a desert again. And they just have to alternate these ecosystems to explain these layers. 5, why are there missing layers representing millions of years of missing time, according to the secular explanations? So right where that red line is between the Muav and the Temple Butte limestone, those are both limestone layers. But according to their geological column, the Muav limestone is much older than the Temple Butte, and they're part of recognizable layers. So I'm not doubting their analysis of that. But the two layers shouldn't be touching. There should be a lot of other rock between them. 6. Why is limestone distributed so widely across the entire globe? If it's a product of a warm, shallow sea, then that means those places up in Siberia and Greenland and northern Canada had to have been in a tropical or subtropical region for a long time in order to build up these layers of limestone from the clams and oysters. 7th, why is there such a difference between old and new limestone? By old limestone, we mean like the Grand Canyon. New limestone is places where it's obviously more recent, very post-flood, maybe only a few thousand years old. So in the old limestone, we have the calcium carbonate looking like calcite, very small grain size, quartz sand grains mixed in, fossils pointing in the same direction, like the famous nautiloid layer where these squid-like things are kind of, a lot of them are lined up the same direction, and fossils of delicate soft-bodied animals like jellyfish or crinoids. In the new limestone, we find that the calcium carbonate looks more like aragonite. If you look at it under the microscope, it has that crystal shape. Grain size is larger. There's no quartz sand grains mixed in, fossils not in the same direction, and there's no soft-bodied animal fossils. 8 is the dolomite mystery. Dolomite is limestone where a portion, or even more than half, of the calcium carbonate has been replaced by magnesium. Whole mountains can be made of this dolomitic rock. Now, dolomite can't form in a warm, shallow sea because marine creatures generally don't use magnesium to make their shells. So, with the warm, shallow sea explanation off the table, the geologists struggle to come up with a scenario for how this magnesium got into the limestone to make dolomite. One theory says after the dolomite was formed that water that had magnesium ions came through the rock and kind of trickled through it, leaving the magnesium ions behind. But how could water have trickled down through something the size of this mountain in a way that produced a very smooth, homogeneous distribution of the magnesium? So it's not patchy like you'd expect, with one area having a lot of magnesium, maybe one area less, like water would kind of trickle unevenly through the rock. It's very homogeneous. And lastly, what about the sheer volume of limestone? Where did all this sediment come from? The amount of sediments that's piled on top of the continents averages about a mile deep. Someplace a little more, someplace a little less, but like on average a mile. Now, about a quarter of it is limestone, and the other 3/4 are sandstone and shale and various other kind of sedimentary rock. So if these sediments all were deposited during or shortly after the flood, that means we need to have a mechanism that can generate a massive amount of sediments in a very short time. So be aware that other flood theories assert that all these sediments were created by giant waves crashing onto the land at the beginning of the flood. The seafloor would heave upwards and create a tsunami wave, and it would hit the land, and that's what eroded the rock. So, is this possible? How fast can a wave erode a rock? So I thought, let's take a look at a place where we know that there's water erosion of rock going on at a very fast rate, and that would be Niagara Falls. The waterfalls are pouring over the limestone 24/7, very high speed, and they have a very high erosional power. Now we know that the maximum rate of erosion ever recorded at Niagara Falls is about 5 feet per year. We have records that go back decades, even centuries, so we know where the falls were, and it's never been more than about 5 feet of rock per year. It's less now because they're controlling how much water goes over. So is it really realistic to say that giant waves crashing onto the rock, even sweeping over the land, can it erode that much rock in a very short time? At the beginning of the flood, we only have a few weeks, maybe a few months to generate all the sediments. And if Niagara Falls can only do 5 feet a year, it's very, very doubtful In fact, I think impossible for waves to generate that much sediment. So the question is, can hydroplate theory come up with some solutions to these mysteries? First, a quick review of initial conditions. Hydroplate theory suggests that the Earth originally had a granite shell, no continents, just a solid granite shell, and underneath the shell there was a layer of water, which was very hot and under pressure. It was supercritical water, and we assume that the water had carbon dioxide in it. Now, this doesn't come out real clearly in Dr. Brown's book, so I checked with some hydroplate advocates, and they studied a little bit and did some math, and they said, yes, it is entirely reasonable to assume that there was a fair amount of carbon dioxide dissolved in the water. And we do see this at the bottom of very deep holes, the deepest holes ever drilled into the crust. At the bottom, there's hot water, and it does have dissolved gases, including a lot of carbon dioxide. So this is a reasonable assumption. The subterranean water would have been under extreme pressure and temperature, causing it to be supercritical, and it would have begun to erode the underside of the crust. Now, carbon dioxide is also very good at dissolving things when it's supercritical. In fact, in industry, supercritical carbon dioxide is used as a solvent. That's what it does really well. So we have two substances that can be eating away at the crust. And as this erosion happened, it would have released many mineral ions into the water. Now you can see a little bit of research that backs up this assertion. So the mineral ions in the water would have been free to float around and recombine in new ways and create new molecules. Now we're going to watch a short video by Brian Nichol showing how this might have happened in the subterranean chamber, with carbon dioxide being recycled as the dissolving process happened.
These minerals were broken down into more basic molecules, elements and ions of sodium, chlorine, carbon, calcium, copper, oxygen, aluminum, magnesium, and iron were all dissolved in solution with supercritical water. In this state, new compounds could form like sodium chloride, or what we know as table salt, and aqueous calcium and bicarbonate ions. All these compounds were dissolved in solution with supercritical water. As temperatures in the subterranean chamber continued to rise, the supercritical water In the case of limestone precipitate, aqueous calcium and bicarbonate ions followed our well-known chemical reaction for limestone. As before, each of the two bicarbonate ions that reacted with calcium carried a carbon atom. Each of these carbon atoms ended up in two new yet different molecules as they chemically reacted. One of the carbon atoms produced solid calcium carbonate, or limestone precipitate, which fell on the chamber floor. The other carbon atom produced aqueous carbonic acid, which, remember, would break down into water and CO2, especially in the high-energy environment of the subterranean chamber. However, because the solution was trapped and sealed deep under the crust, this new carbon dioxide molecule could not escape up into Earth's atmosphere. Therefore, hydroplate theory solves the huge question of why Earth has over 1,000 times more limestone than it does carbon dioxide. Since the CO2 produced during precipitation of limestone could not escape, it simply dissolved back into solution with the supercritical water. Of course, this CO2 itself was in a supercritical state within the confines of the chamber, so it too aided in further dissolving of the granite and mantle materials that made up the chamber's ceiling and floor respectively. As with supercritical water, each carbon dioxide molecule produced stood a good chance of being further broken up into ions. In these conditions, eventually the components of any CO2 produced would themselves combine with stray hydrogen and oxygen ions, which were in abundance, and form yet another bicarbonate ion. This new ion then became source material for yet another limestone reaction. Rather than escaping, the extra carbon was used over and over again to dissolve more and more material and produce more and more limestone. Each cycle produced more and more limestone precipitate on the chamber floor. With each cycle, the percentage of carbon locked in limestone increased and became more and more lopsided. Thus, in this contained environment that hydroplate theory presents, we see a straightforward solution to what at first seemed like a huge mystery of missing carbon when thinking of limestone formation as occurring on Earth's surface. Hydroplate theory provides the solution explaining how vast amounts of limestone was produced and deposited while at the same time very little CO2 was generated in the process.
Now, someone might ask the question, is there any actual evidence that minerals can precipitate out of supercritical water? And the answer is yes. This photograph was taken by scientists who were studying supercritical water, and they were watching in real time little white flecks appear in the water as the minerals were outsalting. They called it outsalting because it looked like salt was coming out of the water from nowhere. So then the granite shell cracked for unknown reasons. Well, we assume a crack started so that the fountains of the great deep burst forth, as it says in Genesis 7:11. The first water probably ended up in space because it was coming out so fast and eventually coalesced into comets, and that'll be addressed in another talk. Now, the eroding power of the fountains was immense, and it could have dissolved a lot of the crustal rock on either side of the opening. This intense erosion of the crust produced even more sediments. So the sediments were a combination of stuff that was coming up and what was being eroded. So the question is, can high pressure water actually erode rock that fast? Well, here's a picture from a video where a 60,000 psi water jet is cutting through a rock like it's made out of butter. So yes, water can pulverize rock that fast. So after the escaping water slowed down a bit, it would have surged onto the surface, bringing massive volumes of mineral slush along with it. So all this preformed calcium carbonate and many other things could come to the surface. Now, some carbon dioxide probably did escape from the chamber, but not nearly enough to poison the earth, probably just enough to help the plants to recolonize the earth. So the mineral saturated water eventually hardened into rock, but before this happened, the minerals had to be sorted into layers. Hydroplate theory proposes that a substantial amount of sorting came about through a process called liquefaction. And so liquefaction really came to the attention of geologists when things like this started happening during earthquakes. Buildings would just sink. Well, it turns out it's liquefaction. So during liquefaction, water flows upward through sediments or soil, allowing the particles to shift their position. So while the sediments are suspended, they're able to shift their position, and particles with similar density or similar size or similar shape or even similar chemistry will end up clumped together. Water happens to be very good at sorting things, and this is just a simple example I saw in my driveway where the rainwater, we had a really large downpour, and it just picked up all the pine needles everywhere in the yard, even in the grass. It washed them into the driveway and then sorted them so that they're even parallel. They all ended up in approximately the same place and all facing the same direction. And even a simple bottle experiment can show how quickly sediments can be sorted by water. You can do this at home with a 2-liter bottle, and you can watch layers forming within minutes, not hours. Now, I know this is just a bottle. This isn't the flood. There's no way we can recreate the flood. But this shows you that water is a very powerful sorter. During the flood, there would have been massive waves traveling around the globe, and underneath a wave, the water was pressed down into the sediments as the water pressure increased. And then in the troughs between the waves, the water pressure was much less, and so the water would flow back up through the sediments and suspend them for a short time so that they would be able to shift their position. And in this way, similar sediments would end up at a similar position. And here's a little animation by Brian Nichols showing this in action. Water goes down, and then a trough comes. The sediments rise. There's an opportunity to shift position. Pressure increases again. They're compacted. And then maybe a new layer of sediment rushes in. So during the next series of waves, mainly the top layer is lifted. The bottom stays in place, and the liquefaction works on sorting the next layer. So you can see that the layers would have been sorted a little bit at a time. Now, at this point, someone might be wondering, is there any actual experimental evidence that minerals can get sorted after they precipitate out of water? And I don't have any great pictures for this one. I just have some references, and these are listed at the end of the outline that I have posted to go with this talk, and you can check them out. So liquefaction, combined with the action of water flowing in one direction, which can also sort things, would have produced very flat and relatively pure layers. New loads of sediments would have flowed in and piled up on top of old ones, but like we said, liquefaction worked primarily on the top layers. Strata like this have repeating units called cyclothems, where we have from bottom up sandstone, shale, limestone, sandstone, shale, limestone. And this order is consistent with the liquefaction explanation. What about the coal layers? The dividing line between limestone and coal layers can be quite sharp. The log mat theories of coal formation put forward by other creationists are very compatible with hydroplate theory. It's in agreement with the other flood theories that coal is made of pre-flood vegetation. But Dr. Brown suggests another factor to consider with the formation of coal, and that is that vegetation could have gotten trapped into flat pockets called water lenses. In the bottle experiments, little water lenses have been observed. Plant material can become trapped in these lenses between layers of sediments. Then after the flood, the trapped layer of vegetation will turn into coal. And the recipe for making coal is plants, a little bit of clay, some seawater, plus pressure and mild heat. And you can form coal within weeks. One interesting connection between limestone and coal is something called coal balls. These are balls of limestone that are found in coal seams. Coal miners hate to come across these limestone balls because they're very hard and they'll jam or break their mining machines. Not all coal balls look round. Here's one that's kind of odd shaped, and they often contain marine fossils. Now, schools of fish might have gotten trapped in large water lenses, and then when the water finally drained out at the end of flood, there'd be a whole school of fish trapped between the layers, and then they'd be pressed and flattened. And here we see a limestone formation from the Green River Formation, where you have millions of tiny flattened fish that are just paper thin between two layers of sediments. So maybe they got stuck in a water lens. In addition to liquefaction, there was another layering mechanism at work, and that would explain these very thin varves. So secular scientists say that each of these lines, one layer, is a year, and then they just count up the lines, and that's how many years. But it's been proven in flume experiments that you can get these thin varves when there is alternation between laminar and turbulent flow, something called the Kelvin-Helmholtz instability. And when that happens, you get these layers forming. Like every minute, a layer can be formed. So this is now an established fact based on experimental observation. So this means that geologists can no longer claim that varves are proof that the Earth is millions of years old. So what does hydroplate theory's answer for how limestone turned into marble and why some limestone layers are tipped? Hydroplate theory proposes the same answer for both of these questions, something called the compression event. At some point during the flood, the continents began to slide because the mid-ocean ridges were being lifted up. Now, the continents could slide because they were riding on a layer of supercritical water, which was almost friction-free. But eventually the water all escaped and rock began sliding against rock, and friction took over, and the plates came to a sudden halt. The crust began to buckle and crush, and the sediments on top would have experienced compression also. Some of the sediment layers rose or buckled, they wrinkled, and some were tipped. These layers of limestone can't have been laid down over millions of years. If they were already old and hard when the lateral compression occurred, they would have crushed and broken instead of deforming like this. Rocks can't bend. They break under stress. Common sense says that these layers were all at least somewhat soft when they experienced compression. Hydroplate theory's solution to the dolomite mystery is that dolomite formed in the same way and at the same time as limestone. We think that mantle rock is made of olivine and peridot, which are high in magnesium and iron. So some of the mantle rock would have dissolved when the supercritical water was in the subterranean chamber. So there would have been magnesium and iron atoms in the water, as well as calcium and silicon and many other things. So as the water escaped and came to the surface, there were some areas that had a lot of magnesium in it, and in these areas, dolomite was formed. And in areas where there was a lot of iron mixed with the calcium carbonate, we got red layers of limestone. And apparently there was enough iron in the water to stain very large layers like the red wall limestone in Grand Canyon. Another famous limestone formation that deserves a mention is the Bahamas Bank. And in the photograph here, the light blue areas are shallow water, the dark blues are deep water. Now the water is shallow in these light blue areas because it's sitting on top of a large limestone platform or bank, believed to be even up to 3 miles thick. And as usual, geologists use the warm, shallow sea explanation because they don't really have anything else. Wikipedia says that the limestone was deposited in shallow water. The only way to explain this massive column is to estimate that the entire platform has subsided under its own weight at the rate of roughly 2 inches per 1,000 years. So if you doubted that I was telling the truth previously, there you got it, straight from Wikipedia. They have to have that just so subsidence to explain limestone. So then they say that after the limestone bank had formed, the situation then reversed, and somehow the bank was elevated instead of subsiding, but they never give a reasonable explanation for how this limestone went back up again. And then while out of the water, then the limestone experienced this erosion, forming these holes and caverns, and then things sank again and the water level rose just enough that the holes were filled up, forming what we know today as blue holes. So the hydroplate explanation of the Bahamas Bank would be that this is an area that was right at the edge of one of the continental plates, and that one of these gushings of material came out possibly near the end of the flood, and it didn't make it very far, and it just kind of dumped right there. And then the shallow lime-rich water around this dump was an ideal place for corals and other marine creatures to live, so organic limestone was made on top of this inorganic limestone. Hydroplate theory agrees with the idea that the Bahamas area might well have been above sea level for a time and experienced all that erosion, because it suggests that right after the flood, the worldwide sea level was much lower than it is now. And what we call continental shelves today were actually the edges of the continents for a time. And so there was a lot of erosion from runoff, creating these submarine canyons. Today they're submarine, but at the time they were out of the water. So it's a mystery as to how these canyons could have formed underwater. Well, obviously they didn't. They formed above water, and then the sea level rose. Part of the reason the sea level rose in the centuries after the flood was that the continents were slowly sinking into the mantle. There was also a lot of post-flood lakes draining off, but the continents were gradually sinking down. And then the rising sea, of course, covered the bank, filled the holes with water. Now, what about chalk? The cliffs of Dover are the most famous chalk cliffs, but there's many others in the UK, also France, Denmark, Ireland. And chalk is also found in the United States in places like Alabama, Mississippi, Tennessee, Texas, Kansas, and Nebraska. There's a nice chalk deposit in Texas. So chalk is what secular scientists want all limestone to be, organic. Chalk is actually mostly organic. It's made of the shells of microscopic organisms. The one on the left is called the coccolithophore, and that tends to be predominant in the cliffs of Dover. There's also little critters called foraminiferans, and you'll find these shells as well. And here's an electron micrograph showing what chalk looks like at the microscopic level. So there is probably some inorganic limestone mixed in with it. There's like a base, an inorganic cement holding together, but there are a lot of these little shells. Now, of course, secular scientists believe this process took millions of years, accumulating a centimeter per 1,000 years, but there's, of course, problems with this idea. If the process of chalk formation was so slow, then why are these deposits so pure? So it's hard to believe that there was never any dirt or clay or anything that washed in while this was, quote, a warm, shallow sea. Even in a young Earth scenario, with chalk accumulating since the flood, still the chalk beds should not be this pure. Secular scientists tried to explain this purity by saying that the chalk must have formed during a very dry era when the adjacent land was desert, extremely dry, and just didn't produce any muddy runoff. But that's obviously just a rescue device. Now, several creation scientists have worked on the problem of chalk, and I found this article at creation.com very helpful. It discusses the pros and cons of each approach, and then offers another solution, and one that turns out to be compatible with hydroplate theory. So all of these little shelled organisms can reproduce very quickly. In a matter of days, they can make an algal bloom. Here we see a satellite picture of a bloom in Lake Erie, and here it looks kind of green, but in around Antarctica, when these coccolithophores have a bloom, it looks white. To get a pure white chalk deposit of this size without any mud or clay in it, you need extremely rapid buildup of algal shells, covering the span of only a few days or at most a few weeks. The blooms must have happened at the end of the flood while the water was still covering this part of the world. This chalk cliff clearly shows individual blooms with a gray hard ground between them. A hard ground is a thin layer of debris and shells that builds up in the time between blooms. The hard grounds emphasize the fact that pure chalk deposits must happen quickly. All chalk deposits do show layers, but none quite as clear as this one. The authors at creation.com quote calculations that indicate that, although we don't see this happening today, it is technically possible to have a bloom large enough to create a chalk cliff in only a few days or weeks. Now, Dr. Brown points out that all the calcium carbonate coming out from underneath the plates could have played a role in chalk formation, providing dissolved minerals that would act not only as building material for the shells, but also as a cementing agent. Secular geologists struggle to explain how these chalk beds could have been uplifted so high above sea level. If they're the product of a warm, shallow sea, that means they were underwater at the time of formation. So we know this land was submerged when they were created. But if they formed at the end of the flood, while the land was still underwater, no uplift is needed. But even if we found a reasonable solution to the problem of how these chalk cliffs could have formed, that doesn't make them any less amazing. They are indeed one of the most astounding and puzzling rock formations on Earth. I hope this presentation has made you a little more interested in limestone, or at least a little less disinterested in it. And if you'd like to know more, I suggest starting with the free ebook that I've posted on the conference page at hydroplate.org. There should be a link to it right underneath the title and description for this presentation. Okay, so I'm going to stop sharing. Are there any questions? I haven't been looking, of course, at the questions.
It's one that is sand basically ground up granite or a wider range of materials, in your opinion?
So one thing I really like to do with my science classes, I teach basically grades 4 to 10. That's my sweet spot. But I have a set of stereo microscopes, and they are the best things. And so we look at sand. So I've seen with my own eyes sand from around the world, and it's every place in the world is unique, every type of sand. But you can see I have them take tweezers and pick out. You can pick out feldspar, mica, quartz. They look like little quartz crystals. You're like, that's feldspar right there, and they make a little tiny miniature rock collection. And so the sand from the Bahamas, you'd find that there's a lot of little tiny shells they can pick out. And the sand from Hawaii, there's some of it sand that has magnetite in it. So when you say sand, there's just a wide range of stuff. But your typical put it in the sandbox sand, yeah, it's quartz and feldspar and mica. And you can see them and maybe some other things, but yeah, it that's what it is. Ground up granite. I mean, a lot of it is.
Thank you. And did black smokers originate from supercritical water?
So my understanding that, as Dr. Brown says yes. That's not something that I've studied in depth, but I believe that is what he says in his book, that it is remnants and somehow. So there was no connection between the water originally, the surface water and the water under didn't have a connection. But all bets are off once that crack opened up. So yeah, probably a lot of it's leaking. It's still leaking up. That's his idea. Yeah, it is. And of
Yeah,
course, it's very, very rich, very hot, and very rich in minerals.
that makes sense. And how do you get diatomites?
Oh,
Diet.
diatomaceous, the diatomaceous earth. Yeah, I've looked at that
Yes.
too. It's really cool. So you also have diatoms, which they have a silicon-based shell. So diatomaceous earth has a different chemistry. It's not calcium carbonate. It's the creatures. Basically, diatoms live in glass houses, and they make it's the craziest things. I love them. They have these little geometric shells they live in, and they're basically made of SiO2, silicon, glass. So diatomaceous earth has a silicon-based chemistry because it's mainly, yes, those instead of calcium-based.
Very interesting. And that dolomite, that was very interesting. Um,
Yeah, so I was at a quarry. I had taught a class about this, and we had discussed the various things about formation of sediments. And it was just interesting to see, my kids are middle schoolers or elementary middle schoolers standing there at the quarry. And the guy actually said that we're looking at that picture that I showed you, this vast quarry of like just unbelievable amount of gray rock there. They're hauling it out with these giant trucks. It's going to take them decades to mine that. And so he's standing there, he's going, yeah, this used to be a warm, shallow sea, and all this came from clams. And my kids are sitting there. Clams did not make this rock. And I could see them. They were just bursting. They were wanting to go, ah. And I was just like, later. And I'll just let them. But it's kind of, a kid's reaction. It's like, oh, really? Come on. Clams made Grand Canyon. Give me a break.
right.
It just,
Right.
uh,
I loved your example about how it had to sink at just the right form or just the right rate to get it that far. And then, hey, what happened to
yeah.
the
And so
basement
it's a
rock?
good point. So you can, and I'd like to, when we talk about uplift, that's not my topic. When I talk about that, so I actually have a little thing. I call it my uplift fairy wand, and it's this little stick with a little string, and I can just use it whenever I want something to uplift. I go ding, and there was uplift. And they say this in the books that the mountains uplifted. They say, well, how? They never provide a mechanism. You can't just say the word uplift and have the world obey, and you can't just say the word subsidence and expect, no, no. You've got to come up with a reasonable mechanism that works, you know, uh, physically, that works, that it's explainable. You can't just toss these words out there.
Yeah, that's what I really liked about that hydroplate theory. It's got the mechanism, the energy, the
Yeah.
forces. It all fits together so beautifully.
As I should point out, like that with the waves crashing on the ocean, when I realized that they're all the other, if you don't have the sediments coming in this way from the chamber or from the degrading of the rock as the fountains came out, where do you get all this stuff? And tsunamis crashing on the beach, you know how often intermittent waves are. I mean, no, we don't. Show me the evidence somewhere that this can happen. I mean, I've shown you the evidence that water can cut rock. You can see it's a small example, but we do have things to back this up. And yet they can make these claims and just get away with it, and nobody challenges them on these claims.
Right. Right. That's what we need enough. We need more people stepping up to the microphone and say, how? How is that
It's
done?
yeah, fine. I mean, if you want it, that's your idea, that's great, but defend it. Show us something. And they don't even have it written down. They have a few talks or presentations on YouTube, but I mean, Dr. Brown is a 600-page book. So how can you say that he hasn't documented his ideas well enough? He's got more footnotes in it than he has actual text. So, we can discuss those, but if they can come up with something like that, then we can have a conversation.
Exactly. Exactly. Very well done.